Hi, I'm Norman Wildberger, and today we're going to talk about laws of arithmetic. This is part of our Foundations of Mathematics series. So I remind you, up till now what we've done is we've first of all established what are the natural numbers. A natural number is just a string of ones, and they form this very natural sequence like this. We have two operations, addition and multiplication. The addition of two natural numbers is just what you get when you combine them by juxtaposing them in the simplest possible way. Multiplication is what you get when you take this many groups of that one. So in other words, for every one in this first number, you put a copy of the second number. So 2 times 3 is 2 copies of 3, one there and one there. And there are various laws. There are the laws for addition, the commutative and associative laws. There are the laws for multiplication, the commutative, associative, and identity laws, and 2 distributive laws. And I left it to you as a challenge last time to try to prove these laws here. We've already talked about these ones, and this one is obvious. So today we want to talk about why these laws are true, and we'll start with the commutative law for multiplication, which says that n times m equals m times n. This is in some sense the most interesting of the laws. Here's an example, 2 times 3. We have two groups of 3. One there and one there. On the other hand, if we think about 3 groups of 2, or 3 times 2, we have 3 groups of 2. Why should it be that 2 groups of 3 is the same as 3 groups of 2? This is already a subtle point. And to explain why, let me change notation just slightly, just temporarily. Instead of using little sticks, I'll use circles for our basic entities. So I've just rewritten, here's 2 times 3, 2 groups of 3. And now what I'm going to do is I'm going to take those circles and I'm going to rearrange them. Instead of putting them all in a row, I'm going to put one group of 3 there and the other group of 3 on top of them. Over here I've got 3 times 2, that's 3 groups of 2. 2, 2, and 2. And again I'm going to do the same thing, I'm going to put them, the first row there, then another row, and then another row. So we have 3 groups of 2 stacked on top of each other. Now why are these two the same? It's because these two configurations visibly have the same number of elements. We get one from the other just by flipping. Our next law is the associative law for multiplication. K times n, done first, times m, is the same as k times what you get when you take n times m. So let's illustrate with an example. Suppose k is 2 and n is 3, and I'm not going to suppose that m is anything in particular, so we'll leave m as general. So we have 2 times 3 times m. So the brackets tell us we need to do 2 times 3 first. There's 2 groups of 3. So we have 2 groups of 3 times m. And I remind you how to multiply. We simply have to replace each one of the ones here with a copy of this thing. So we have altogether m when we do this way. When we do it in the other way, it's 2 times 3 times m. So that's 2 times, what is 3 times m? It's what you get when you replace each of the ones here with an m. So m. We get 2 times m, that means we replace each one of these with a copy of those, so we get m. And we can see that we get the same thing, because in each case what we're really getting is 2 times 3. There's 2 times 3 of them there, and there's 2 times 3 of them there. And what m is immaterial. It will always be equal. Even if we don't use 2 and 3, use 3 and 4, or 4 and 5, or anything else. Now the distributive laws, which combine addition and multiplication. So the first one is k times n plus m equals k times n plus k times m. And I remind you, this means we do this multiplication and this multiplication before we do the addition. Let's look at an example. Suppose k is 3, n is 2, and m is 1. Then k times n plus m will be 3 times, well, this sum is 3. And I've written the 3 in a way that keeps track of where the ones came from. So these two I'll mark in red, and this one in green. So we have 2 red ones and 1 green one. And we're supposed to take 3 times that. So we have one group, another group, another group. Now we are going to rearrange those. We're going to take all the ones of the same color together. So there are 3 groups of 2 red ones. We'll put them all together there. And we'll bring all the green ones, there's 3 ones, over that side. And we see that what we end up having is, in terms of the red ones, is 3 times 2. So we have 3 groups of 2 red ones. And also we have 3 groups of 1 green one. So 3 times 2 plus 1 is 3 times 2 plus 3 times 1. And this argument shows why it's true in general. We can always do this kind of rearranging to convert this to this. Alright, what about the other distributive law? We could do it in the same way, but let me illustrate another way of thinking about it using the laws we've already established. If we have k plus n times m, we can use the commutative law to rewrite that as m times k plus n. It's just the commutativity. And now we can use the distributive law we've just proven to write that as m times k plus m times n. And each one of these two products can be rewritten using the commutative law. So that becomes k times m, and this one becomes n times m. And that's what we require. So we have now proven all the laws of arithmetic so far. These are the main laws of mathematics. And I think you can see that the arguments are simple enough that with some patience you could explain it to a 10-year-old boy 100,000 years ago. So is this the standard way that mathematicians think about the laws of arithmetic? No, it's not. Most mathematicians believe that mathematics is founded on modern set theory. And they follow John von Neumann's suggestion that we should define the natural numbers in terms of set theory. 0, which we haven't talked about, but which represents nothing, is represented by the empty set. That's reasonable. 1 is represented by a set which contains one element, namely the 0 that we've just defined. So it's a set that contains within it the empty set. Also, we can't argue too much with that. However, then the idea is that all subsequent numbers are defined as sets of previous numbers. So 2 is defined as 0, 1, which is this, and 3 is defined as the set 0, 1, 2, which is this, and 4 is defined as the set 0, 1, 2, 3, and so on. And it gets more and more complicated very quickly. So this is a very complicated, it's overly complicated. It's certainly unintuitive. It doesn't correspond to the way people think about numbers. And it's really divorced from reality. It's an aspect of the way modern set theory has really distorted the entire discussion about foundations of mathematics. Modern set theory gave rise to the new math some 40, 50 years ago, which we all know now was sort of a disaster. But less well known is that it's also contributed to very shaky and complicated foundations for mathematics. One of our aims in this series will be to look very critically at other deficiencies in modern set theory and to suggest, as we've done here, replacements, some simpler ways of thinking about the fundamental concepts. Next time, subtraction and division, the other two main operations in arithmetic. I hope you'll join me. I'm Norman Wildberger. Thanks for listening.